Yeah. Oh, yeah. I thought I was replying clearly, but obviously I wasn't. That you can't. This is about the tan theta. Tan theta 1 minus tan theta 2 is not tan theta 1 minus 2, theta 2. So when I asked you, did you mean, that you're going to change those tan thetas in that way, you can't do that. So maybe I'll explain at the end of the class. Yeah. But yeah, I didn't say that clearly. I just said, did you do this? But what I should have said is, you can't do this. Okay, yeah. Okay, I'll get started. We've been taking this grand tour of light's properties. This is the last class on light's properties. Next week, we'll be taking a tour of space and time and looking at the properties of space and time. This class will join together the properties of light with the properties of space and time. I want to discuss these three bullets today. I want to introduce what's known as the Michelson interferometer. It's a device that involves interference of light. It's a device that's used to measure very, very precisely wavelengths of light. It's a device that's used to very, very precisely measure small distances, short distances. It's also a famous device that was deployed used to detect a material called the ether that was thought to exist. Turns out it does not exist. And so the Michelson interferometer was one of the most famous experiments that actually failed but led to a very important discovery. Anyway, we'll walk through these items. So, firstly, let me just introduce the Michelson interferometer and how the Michelson interferometer works. Interferometer, it just means that it's based on interference. This picture here, it's really a beautiful picture, I think. This is a real picture of a real interference pattern from a real Michelson interferometer. So what you're seeing here are rings of constructive and destructive interference of light. The red rings are the constructive interference, where light is beams of light are interfering constructively. The dark regions are the destructive interference, where light beams are interfering destructively. So Michelson was a U.S. scientist, worked in the U.S. scientist more than 100 years ago, and more than 100 years ago he got the Nobel Prize for developing this instrument and deploying this instrument to measure the speed of light. And we'll see over the course of this class and the next classes why it might be that Michelson, who built an instrument and then measured the speed of light, would get the Nobel Prize for that. So just to remind you once again, the ingredients that we need for understanding today's class and the Michelson interferometer are interference of waves, specifically constructive interference, which occurs if these two waves interfere constructively. It means that they're in phase, crest meets crest, trough meets trough, and we make a larger superimposed wave out of the two individual waves. And then there's destructive interference. That's when two waves combine where they're out of phase. Here they're completely out of phase, 180 degrees out of phase. So here crest meets trough, trough meets crest, and these two waves coalesce, interfere to make a much smaller wave, and that's over here on the right. So it's just these two ingredients again. This is the idea behind the Michelson interferometer. This is the basic concept of the Michelson interferometer. It takes a single beam of light and it breaks or splits that beam of light into two separate beams of light. And then it recombines those two separate beams of light into a single beam of light. So that's basically how it works. It's a clever arrangement for breaking a beam of light in two and then recombining the beams of light back into one. So what does that do? That creates a interference pattern between those two split beams. And that interference pattern is similar to other cases where we've combined two beams of light or two sources or origins of light. One was the two-slit interference, and the other one was the soap bubble interference. In both of those, whether it was through two physical slits or whether it was from the inner and outer surfaces of a soap bubble, we were combining two sources of light and looking at the interference, and the Michelson interferometer is also combining two sources of light and looking at the interference pattern. So as I mentioned, it's used all the time for in labs. It's used for measuring wavelengths very precisely. So you might want to know very precisely the wavelength of some particular light. It's used for that. It's also used for measuring distances very, very precisely. There's a fantastic example of it, LIGO experiment, I'll mention it later on, that measures distances unbelievably precisely with the Michelson interferometer. But it also led to, and this was just by accident, serendipitously, a crucial discovery about light, and that led to, again, accidentally, a crucial discovery about space-time. The discovery was that light has a very strange property that it has the same speed to all observers, every observer, and that fact led to a new understanding of the nature of space and time on which the speed of light is built. And so we're going to discover this towards the end of today's class. Okay. More specifically, how does the interferometer work? Because I just said it splits a beam into two and then it recombines the beam into one. You see the interference pattern. That all sounds pretty simple. Here's how it works. So this is a sketch of how it works. This is like a helicopter view looking down on the interferometer, and this is a description of how it works over here on the left. So what do we have here? We're going to start at the light source. That's the origin of the beam of light, and then we'll work our way to the scientist here in the lab and the observation of the interference pattern. Okay, so we have a source of light, let's say laser light, and that single beam of light is directed to this object here. It's a partially silvered mirror. So what's a partially silvered mirror? Partially silvered mirror is something that partially reflects light, like a mirror, and partially transmits light, like a window. So it's a partially silvered mirror is a code word for something that will reflect, say, half the light and transmit half the light. And so that's actually what happens here. Half the light is reflected off this mirror. It came in towards the right, it's bounced up towards the top, and half of it's transmitted. It came in towards the right and it continues towards the right. So we split the beam in two with the partially, so that's how we split the beam in two. That's how we divide the beam into these two parts. Okay, so some of the beam is going upstairs now, and some of the beam is continuing to the right. And the beam that goes upstairs strikes another mirror upstairs here. This is a 100% reflecting mirror, and the beam that went to the right strikes a second mirror over here. That's also a 100% reflecting mirror. So these light rays strike these two beams. These light rays strike these two mirrors. I label them M1 and M2, and they reflect the light back towards that partially silvered mirror again. So here's one light ray went up and came back down in red and magenta here, and here's one light ray went right and then went left, and again it's coming back to where it started on the partially silvered mirror. Then the partially silvered mirror reflects, and it actually reflects a fraction of both of these light rays back down towards the bottom of the screen here. Now we're recombining the two rays that went the two different paths, upstairs and to the right, and this is where you get the interference pattern. And here we are looking at that interference pattern of bright fringes, dark fringes, constructive, destructive interference due to the light rays. There's one thing I didn't mention here, this piece of glass here, this plate of glass here, that's just added so that both light rays travel through the same thickness of glass. You see the light ray that went up and then back down traveled through an extra thickness of the glass of the partially silvered mirror here. And so we've added that thickness of glass to the passage of the light ray that travels right then left. And so it's just a technical detail really to make the paths of the light ray that went up and down and right and left to be as equal as possible. This whole thing involves all of the things that we've been talking about over the past couple of weeks. So it involves reflection, it involves refraction, it involves interference, it involves diffraction. So everything's incorporated into this. It's a full story. Okay. Okay, so how's it used? I said you can measure wavelengths very precisely with the interferometer. I said you could measure also distances very precisely with the interferometer. So how do you do that? One of the mirrors, and I'm going to imagine it's this one upstairs here, M1, is movable. And you can move it very finely, adjust it for its position very finely. The interference pattern, whether you get constructive or destructive interference, say at the very center of this interference pattern, that's determined by the path differences between the light ray that went up, I'll call that light ray number 1, and then came back downwards, and the light ray that went to the right and then came back to the left. I call that light ray number 2. Their paths were L1 and L2 here in this little picture. So whether you're going to get constructive, destructive interference, say at the center of the pattern, depends on the path differences between the route up and down and the route that's right and left. Supposing I was to move this mirror upstairs here, I'm going to move it a distance, I'll call that distance d, that corresponds to a quarter of a wavelength. So I'm going to move that mirror by a quarter of wavelength. Nothing else is going to change. I'm going to move the mirror by a quarter of wavelength. That means that the path of the light ray that went up and then back down, that's going to change by half a wavelength. If I move the mirror closer by a quarter of a wavelength, then it's going to get to it in a shorter distance, and it's got to get back to the partially silvered mirror in a little bit shorter distance. So the total change in distance for the light ray is going to be half a wavelength. If I change the path of this light ray by half a wavelength, but I didn't change the path of the left-right light ray, I'm going to change from constructive to destructive interference, or from destructive to constructive interference. So I'm going to change from a bright fringe to a dark fringe, or a dark fringe to a bright fringe. And so I can see the movement of the mirror by the change in the fringes, from bright to dark or dark to bright. If I was to move the mirror by half a wavelength, so supposing I move that top mirror by half a wavelength closer to the partially silvered mirror, then the light that went up and then down travels one wavelength less in making the complete flight up and down. That means I would go for, if I was starting with a bright fringe, constructive interference, I'd go through one complete cycle and get the next bright fringe, or constructive interference. If I was starting from a dark fringe, I would go through a cycle as I move the mirror and get to the next dark fringe. The way you measure the wavelength of light is you move the mirror a known distance. So I would move it, a micron or 10 microns, some known distance. I would count how many cycles of fringes I went through, how many times it cycled, from bright, dark to bright again, from dark to bright again. I count those number of cycles, and from that I can determine the wavelength of the light. Measuring, moving the mirror a known amount, counting the cycles, I can determine the wavelength of light. Conversely, supposing I knew the wavelength of the light, I wanted to measure a distance, the length of something like an amoeba or a bacterium, I would move the mirror, the length of the amoeba. I would count the number of cycles of bright and dark fringes again, and if I know the wavelength of light, I can calculate the distance that I move the mirror. So there's two ways you can use it. You can use it to measure wavelengths of light, and you can use it that way if you move the mirror a known distance, or you can use it to measure unknown distances if you know the wavelength of the light. And both of them are based on counting the numbers of cycles of the fringe patterns. That's what, as an operator of the interferometer, you'll count these cycles, and then you'll use that to find the unknown wavelength or the unknown distance based on the known distance or the known wavelength. Okay. Here's a picture of a real interferometer. So here's the light coming in on the bottom left. It strikes the partially silvered mirror. Some of it's reflected towards the left over here, some towards the back over here. There's mirrors, 100% reflecting mirrors, M1 and M2 here, that reflect the light back. That light gets combined, and over here, if we were to look at this light, this combined light from these two different paths, we would see the interference pattern. One of these mirrors is adjustable here. You see a little knob at the back here. You can move that mirror closer or further away. So that's how you operate it. Okay, let me just show you a video. So here's another interferometer. Over on the left is the laser beam. Here is the beam splitter. So this is what divides the beam into two, the laser beam into two. There's one mirror at the front here. There's one mirror over on the right here. These are the two mirrors that make the two paths for the light. So here we're going to see my assistant is going to show you how you measure a wavelength of light. And we're adjusting, look, he's adjusting the position in the mirror, and look, these are the changes in the fringe patterns. We see these cycles of bright and dark and bright and dark, and we just have to count these cycles to determine the wavelength of the light. we're going to see some details of this. I don't really know that we need to see these details, but apparently this is one way of counting the fringes. You mark with tape on the screen here where the fringes are, and then you just count the number of cycles that go through that region of tape. And so with this device, you can really, by counting these numbers of cycles, you can super precisely measure wavelengths, you can super precisely measure distances. Here's just a animation of what's happening here. Here came in the laser beam light from the left. We split it into two. It's not two different colors, obviously, now. It's just two different paths they're showing us. It bounces off the mirrors on the left and on the right and on the bottom, and then it's recombined up here. And here you see where you'd get constructive interference because the two combined rays were in phase. Now we're going to do the same thing, but we changed the position of a mirror by a quarter of a wavelength, as I mentioned. So now we've got the two rays going to the right and going to the bottom again. They're reflected back. We're going to combine them here. But now you see that they're out of phase, and we will get a dark fringe, destructive interference. Okay, so let's look at a little calculation involving the Michelson interferometer. In this particular problem, we're going to figure out the wavelengths of some particular light from some particular source that's directed into the interferometer. So this is an example of measuring the wavelength of light. In this case, we're told that we moved the mirror a particular distance. So to measure the wavelength, you've got to know the distance you've moved the mirror. And we moved it 382 micrometers. So micrometers 10 to the minus 6 of a meter. So we're moving it by a very small amount. This is a fraction of a millimeter, about 0.4 of a millimeter, 382 micrometers. And when we did that, we were very patient. We counted 3,400 bright to dark shifts in the fringe pattern. So from this, we're going to calculate, I'll do it on the, whatever it's called, document camera. We're going to calculate the wavelength of the light. There's actually kind of two ways I could do this. We were told that there was 3,400 bright to dark shift changes. That's equivalent to half of that, 1,700 complete cycles from like bright fringe to bright fringe. So I could either work with the fact that a shift from bright to dark corresponds to a movement of the mirror of quarter of a wavelength, or, and there's 3,400 of those, or I could work with 1,700. There's 1,700 changes from bright to bright, which corresponds to the movement of a mirror of half a wavelength. Either of them is fine. I'll just do the case of the 3,400 bright to dark changes. Okay, so let me write down the quantities I know here. Yeah. Move the mirror 382 micrometers, 0.38 millimeters. So, you know, a distance that we could see. We had a large number of bright to dark or dark to bright changes, fringe shifts, 3,400. I call that number n. We said that, if we go back to the explanation how the device works, the relationship between the distance that we move the mirror and the wavelength of light is that if we move the mirror by quarter of a wavelength of light, lambda over 4 here, That, if we move the mirror by that distance, that would be one bright to dark or dark to bright fringe shift. If we move it by 3,400 n, this would be therefore the relationship between the distance that we moved the mirror and the wavelength of light. So we're going to use this little formula here, and we're just going to turn this formula around as a formula for the wavelength. So I've got to multiply through by 4, divide by n, and then fill in the numbers. We got 4 times, we got 382 micrometers. Divided by the number of bright to dark or dark to bright fringe changes, that's 3,400. And then I already worked this out. This comes out to be 0.449 micrometers. 0.449 micrometers is 449 nanometers. That's a wavelength of electromagnetic radiation that's in the visible. It's between 400 and 700 nanometers. That would be, it's a short wavelength of visible light. That would be kind of a blue-colored light. And so that's an example of using the Michelson interferometer, moving the mirror a known distance. We knew the distance we moved the mirror. When we operated the instrument, we counted the number of fringes, 3,400 changes from dark to bright or bright to dark, and used it to calculate the wavelength of light. This is an example, I'll just do this one quickly, of using the Michelson interferometer to measure a known distance. So supposing you've captured an amoeba or some sort of bug or bacterium, right? You could tape it down on your interferometer, fix it there somehow, and then you could move your mirror from one end of it to the other end of it. And if you know the wavelength of light in your interferometer, we just measured it, and we count the number of fringes from dark to bright, bright to dark, or the complete cycles from bright to bright and bright to bright again, we can calculate, we can determine the length of the amoeba. How big is an amoeba, or whatever it happens to be. So let's do that. In this example, we're told we got a different interferometer, because this one has red light, 650 nanometers. That's relatively long wavelength visible light. We're told that when we move the mirror from the head to the tail of the amoeba, or whatever they have, there's a change by 310 dark to bright or bright to dark fringes. Let's use that information to calculate the length of the amoeba. Okay, so I'm going to do that. What do I know? Good question. I know the wavelength of the light. It's 650 nanometers, nice red light. And I know the number of fringes. We went dark to bright or bright to dark 310 times, just to, change it up a little bit. Let's say that, we went 310 times dark to bright, bright to dark. We went half of that, so half of 310 is 155. 155 complete cycles of bright to the next bright, to the next bright, to the next bright. So I'm just going to do it a slightly different way. $155. We could perfectly do it the other way too, but I just wanted to change things. Well, again, we need to go back to our equation that's based on the understanding of the interferometer. If I move the mirror by half a wavelength, we said, then that will change the path by a whole wavelength, which means you would go from, say, a bright fringe to the next bright fringe. So half a wavelength corresponds to a distance that is a movement of the mirror by half a wavelength corresponds to one fringe. If we multiply by the number of complete cycles of fringes, then that is the relationship to the distance we moved the mirror. So I'm going to use this equation here. This time I don't even need to rearrange anything, do I? Because I'm measuring the distance rather than the wavelength. So it's just, I don't know why I'm writing it out again, but just out of habit. N is 155. Lambda is 650 nanometers divided by 2. And then if I multiply these two things together, I got, I'm going to change the units here. I'm going to write it in microns. I got 50.4 micrometers. It was 50,000 nanometers, roughly. And so that's the length of the little whatever, amoeba or whatever it was, I stuck tape down on the Michelson interferometer and moved the mirror from the head to the tail. Okay. Quiz question. Let's do that. Where am I going? So in this quiz question, we're told, again, we were measuring the length of some biological object. People seem to be doing that. We decided to decrease the wavelength of the light. We were using red light in the example. Now we're going to decrease the wavelength to blue light. So that's shorter wavelength. If we do that, will we see the same number of fringes as we move the mirror from one end to the other end of the amoeba? Will we see more fringes? Will we see less fringes, fringe changes, cycles? And so that's the question. Okay, let me give the solution to this quiz question. There's a couple of ways you can think about it. You could think about the formula that relates distance, the mirror is moved, say on the left-hand side of the equation, to the wavelength on the right-hand side of the equation, and the number of cycles on the right-hand side of the equation. So you could think about that formula, or you could just think about, if you get one cycle from bright to dark to bright, that means you've moved the mirror by half a wavelength. You've displaced the mirror by half a wavelength. If you change the light wavelength to a shorter wavelength, then that bright to dark to bright cycle will correspond to a shorter distance moved by the mirror. And so you're going to have to move through more cycles to get from one end of the amoeba to the other end of the amoeba. So with shorter wavelength, a cycle corresponds to moving the distance of the mirror a smaller amount. A longer wavelength corresponds to moving a cycle corresponds to moving the mirror a greater amount. This is probably, certainly currently, the most famous, the most amazing Michelson interferometer. This is not a tabletop Michelson interferometer. This is, you've probably heard it in the news, LIGO interferometer. It's a Michelson interferometer. It's the interferometer, the Michelson interferometer that has detected gravity waves. So gravity waves are waves, not of light or sound or water, but they're waves in space and time. They're waves of the fabric of space and time. And they were first detected a few years ago with a giant Michelson interferometer, what's called the LIGO interferometer. So here's a picture of LIGO interferometer. This path here, this is a mile long. And this path here is a mile long. These are the two paths at right angles that the two rays travel, light rays travel, laser beam light travels, up and back here to the left, up and back here to the right. So there's a laser that's split into these two paths and then recombined, and you look at the interference pattern. Now, we said that, we use the Michelson interferometer to measure wavelengths precisely if we know the distance the mirror's moved, or we can detect how much we move the mirrors if we know the wavelength precisely. That's how this LIGO interferometer works. It's so precise that it can measure a change in the position of the mirrors to 1 part in 10 to the 19. So that's wrong. So, to 10 to the minus 19 meters. So the size of an atom is sort of the scale of 10 to the minus 9, 10 to the minus 10 meters. The size of a proton inside the nucleus of an atom is 10 to the minus 15 meters, something like that. Proton actually isn't a point. It has some size, 10 to the minus 15 meters. This device can measure the change in the position of its mirrors to 10 to the minus 19 meters. So that's 10,000 times more precisely than the size of a proton. Is 10 billion times more precisely than the size of an atom. So it's an incredibly precise way of measuring the displacement of the mirrors. And that's how gravity waves were detected. Gravity waves wobble the mirrors in space and time, and they saw the wobble of the mirrors from gravity waves, from exploding stellar objects, black holes, gobbling up, I don't know, supernova or whatever was happening out there. But those waves that were created in space and time moved the mirrors in these devices, and at that level, 10 to the minus 19 meters, and that was detected. Okay. The last part of today's story is all about and the other famous use of the Michelson interferometer, beyond measuring wavelengths of light, sizes of amoebas, and detecting gravity waves. The original most famous use of the Michelson interferometer, which was to measure the speed of light. And I want to show you how you can use an interferometer to measure the speed of light. And in particular, I want to describe how the interferometer was used to measure the speed of light in the material that it was thought that light traveled in. Okay, the basic idea, as you know, as we've talked about, light is an electromagnetic wave. It's an example of electromagnetic wave, like there's radio waves, like there's microwaves, like there's ultraviolet, and those waves are all predicted by electromagnetic theory. It's interesting, at the time of electromagnetic theory, we knew about visible light. When electromagnetic theory came about, and it said that, well, it predicts electromagnetic waves, and visible light was an example of that, it was realized, oh, hold on, electromagnetic, visible light is just a tiny fraction of the electromagnetic spectrum. There's going to be all sorts of other light that we can't see. For the first time, we realized we're just seeing this tiny narrow slit of light from 400 to 700 nanometers. That unleashed the discovery of, you know, ultraviolet, infrared, radio waves, microwaves. That kind of revolutionized everything. So it opened our eyes literally to the fact there's lots of light, frequencies of light, wavelengths of light we don't directly see, and changed our lives. Well, that's getting away from the point. I wanted to say here one thing about waves. Ocean waves. Ocean waves, we know, they travel in the ocean. That's a medium that carries them. Without the ocean, there would be no ocean waves. Sound waves. Sound waves, typically we would think of sound waves traveling in the atmosphere, in the air. The air, the atmosphere, is a medium that carries the sound waves. If you put a bell in vacuum, there's no sound. You won't hear the sound. So we think of, and you know, the scientists at the time think of that were thinking about waves understood that waves travel in a medium, a material, water waves in water, sound waves in atmosphere. Therefore, light waves or electromagnetic waves must be traveling in a medium. And they called it ether. And so, well, we know about water, that water waves travel in. We know about the atmosphere that sound waves travel in. But this ether that the light waves were traveling in was undetected. And so there became, over 100 years ago now, there was this big search started, the search for the ether. Where is the ether? Where is this medium material that light travels in, and electromagnetic waves travel in? There were some interesting things about it. Let me mention this second and third bullet here. So, you know, water waves, sound waves travel at relatively everyday velocities. So, you know, water waves, certainly everyday velocities is meters per second scales. And sound waves, it's relatively everyday. It's a few hundred meters per second. It's not an unimaginable velocity. On the other hand, light waves travel at an unimaginably fast speed. It's 3 times 10 to the 8 meters per second. So that's 300 million meters per second. It's an incredible speed. That has consequences. If a wave travels at an everyday speed, you know, light waves at water waves meters per second, sound waves at hundreds of meters per second, then it's everyday forces, everyday scale forces in newtons that you need to vibrate the medium that those waves travel in. If waves travel at enormous speeds, you need enormously large forces to vibrate the medium, the ether, that the light travels in. So there was a real puzzle here about the mechanism of how light traveled in the ether compared to the mechanism of how waves traveled in oceans or in atmospheres, sound traveled in the atmosphere. In the cases of ocean waves and sound waves, it was understood that to travel at these particular speeds of the sound waves or the water waves, you need particular size forces to vibrate the water or the atmosphere in which the waves were traveling. But for when you applied those ideas to the light moving through the ether, the enormous velocity of the light waves implied enormous forces exerted by the ether. But hold on, you know, the Earth is moving, presumably moving through the ether. We're moving through the ether. You and I are moving through the ether. If it takes enormous forces to move the ether, why don't we don't even notice it? We just move freely, easily through the ether. So that was a real puzzle. You know, it seemed from the speed of light that the ether must be the most incredibly rigid, strong material there is beyond anything that's known. On the other hand, our everyday experience is, you and I, obviously we walk through the ether without any problem whatsoever. So what's going on here? Okay, so the idea was to detect the ether, this is Michelson's idea, detect the ether with the Michelson interferometer. And I want to show you how you might do that. And I'm going to show you how you might do it by, again, this analogy between light waves and sound waves. Light waves traveling in ether, sound waves traveling in atmosphere. We want to observe the ether that the light waves are traveling in. The analogy is how we might detect the atmosphere, the air, that sound waves are traveling in. Now, of course, we don't need an experiment to detect the air. We all know about the air in the atmosphere. But we do need an experiment to detect the ether because we're curious about that. We don't know about that. But using sound to detect the air is an analogy to using light to detect the ether. That's the analogy we're drawing here. So here's how you might use sound and the speed of sound to detect the air, the presence of the air. So the key point is that we say that sound travels at a speed in air of 340 meters per second. Maybe it's 343 or 341 meters per second. That's the speed of sound in air. If you're moving through the air, so if I'm walking left or right or in the car or in a plane, moving through the air, then if I was to measure the speed of sound as I move through the air, I would measure a different speed. So if I am in my car here and I'm approaching the source of sound, so I'm traveling towards the left through the air, I would see these sound waves approaching me faster as I move through the air. You know, if I was traveling away from the source of sound through the air and traveling away from the speaker, then I would see the sound waves approaching me slower. So an observer moving through the air will see the sound moving with different speeds depending on the observer's motion through the air. This is a very famous effect. It's called the Doppler effect. You actually all experience the Doppler effect. For example, when a fire truck goes past or an ambulance goes past, the siren, if you listen to the siren, when it goes past you, i.e. when it was approaching you and then starts receding from you, you'll notice a change in the frequency of the siren. And that's a consequence of the Doppler effect. It's a consequence of the change of the speed of the sound waves as they're receding from you and approaching you. So it's the Doppler effect is this sort of effect, and that's what we're seeing here. Well, so if you were to measure the difference in speeds as you approach the speaker and as you receded from the speaker, you could infer the presence of air, the material that the sound waves live in. So, of course, we know about the air. We don't need to do this. But this would be a way of detecting the presence of the air, the presence of a medium in which the sound waves move in, by moving through the air and seeing the speed of the sound waves in the air change. So we can do exactly the same for light. So now I've got a source of light rather than a source of sound, so a flashlight rather than a speaker. Instead of my car, because light waves travel so fast, I now need my spaceship. But if I move through the ether now rather than the atmosphere, if I move towards the light source, and I'm approaching the light rays, I'm kind of running into them, I'm going to see them approaching me faster. If I run away from the light source in my spacecraft, running away from the source of light, then I'm going to see that light ray approaching me slower. The scale of the effect is very different, right? Because the speed of light is 300 million meters per second. So here's the speed of light. Here's the speed of light on the left here. When I approach the light source in my spacecraft and see the higher speed, it's going to be a very small change in the speed. So it's a very small effect compared to the Doppler effect in sound. If I recede from the light source and I see a slower speed, even if I'm traveling at this really fast speed, 30 kilometers a second in my spacecraft, it's going to be a very small fractional effect because light travels so fast in the ether. But anyway, if I could measure this change in speed, then I see this change in speed, that would infer the presence of some medium that I'm moving through, the ether, in which the light travels at light speed, and if I move through that medium towards the light source, I would see the speed being higher. If I move away, I see the speed being lower. So this is just the same Doppler effect, kind of like when the ambulance or the fire truck goes by, but instead of listening to the sound and the change in pitch of the sound, maybe I'm looking at the color of the flashing lights on the fire truck and the ambulance, and they would change a little bit. They would change a tiny bit. But it's just such a tiny change that we'd never notice that. But with the interferometer, we could maybe measure this. So this is the idea. Here's an analogy to it. I do like, for some reason, lifeguard analogies. We've had it before. Here's another one. Here we've got a lifeguard swimming in the ocean. And, you know, in the ocean, the ocean water is, you know, flowing maybe from one end of the beach to the other end of the beach, from north to south or south to north, or whatever it is. There's some flow of the ocean. I could detect the flow of the ocean by asking the lifeguard to jump in the water, swim, you know, north to south along the length of the beach, then swim south to north along the length of the beach. In one direction, the lifeguard is swimming with the flow of the water, so kind of swimming downstream. In the other case, he would be swimming against the flow of the water, swimming upstream. In the one case where he swims downstream, I would observe him from the beach swimming faster. In the other case where he swims upstream, I would observe the lifeguards swimming slower as he swims against the flow of the water. And by measuring those two speeds at which he swam north to south and then south to north, they're different. By measuring those two speeds, I could detect the presence of the ocean. Well, of course, I can see the ocean, but I could also see this, measure or determine the speed of the flow of the ocean from the two speeds that I measured the lifeguard swimming at. So this is the basic idea of the experiment we're going to do. I could detect the motion of the ocean. I can detect the ocean's motion by measuring the lifeguard's speed as the lifeguard speeds downstream, faster, as the lifeguard swims upstream, slower. Those speed differences would infer the motion of the ocean. Okay, so you can do exactly that with the interferometer. You could do it with a sound Michelson interferometer to detect the atmosphere. you could do it with a light Michelson interferometer to detect the ether. This is a slide that corresponds to using a sound Michelson interferometer to detect the motion of the air and detect the air itself. So here we got a loudspeaker as the source of the sound waves. We split those sound waves in two with a partially silvered sound mirror. So here's the up-down path, here's the left-right path. If we move the sound interferometer through the air, we will, if I move it left or right, this sound traveling to the right, then traveling back to the left. This is like the lifeguard. This sound is like the lifeguard. If it's swimming downstream, it'll travel faster. If it's swimming upstream, it'll travel slower. This will change the fringe pattern. We can measure the motion of the sound through the air by the change in the fringe pattern. And so we can detect the air. And the idea was to do exactly the same thing with the light interferometer. With the light interferometer, we're going to try and detect the ether. Again, we have a source of light, the flashlight over here. We split it into two with the partially silvered mirror. Some goes up and some goes down. Some goes right and some goes left. If I move the light interferometer left and right, indicated here, then I'll be changing the motion of the light through the ether. The light will be kind of like the lifeguard again, either swimming with the flow of the ether, it'll travel faster, or swimming against the flow of the ether, it'll travel slower in our interferometer, and we'll see a change in the fringe pattern. So this was the idea of how to detect, how to observe the ether. As I say, you could use a sound interferometer to detect the presence of the atmosphere in which the sound waves travel, but we already know the atmosphere is there. We're using the light interferometer to detect the presence of the ether, which we have questions about whether it's really there. So this experiment was done. I won't go. I put up here because I have this thing about wanting to tell the complete story all the time. This is how you understand how the interferometer works. In this little sketch here, right, to understand how the interferometer works for measuring the effect of moving through the ether, you have to work out the geometry and the speeds for the light rays that go up and down and go left and right as you move the interferometer through the ether. So you have to do that, and that's all this stuff is. The end result, the important thing is the end result down here. The end result is that if you were to move the interferometer with some speed, I called it V, through the ether, the fringe pattern would change by some amount, and I called that amount delta. So this is the fringe shift. This is like the number of dark to bright to dark fringe changes. That's the delta. And this V here in green, this is me moving the interferometer through the ether. This is the speed that I'm moving the ether, moving the interferometer through the ether with. And this is the relationship between how fast I move the interferometer through the ether and how much fringe shift I get. And as I say, it came out of, it's just a little bit of geometry to calculate how the fringes change based on the speeds of the light rays in all the different paths, up and down and left and right. But anyway, we end up with this equation. So let me explain the details of this equation. In this equation are two quantities that describe your interferometer. One of them is the wavelength of the light that you're using in your interferometer. So that matters. It mattered when we were measuring the length of an amoeba. L is the length, lambda is the wavelength of light you're using in the interferometer. L, that's another thing about the interferometer. This is the length of the arms of the interferometer. So we saw a video of an interferometer that had arms that were fractions of a meter. We saw a picture of the LIGO interferometer that had arms that were a length of 1 mile. So this is the length of the two arms. So these are the two things. If you go home tonight and you build an Michelson interferometer, you'll build it using some wavelength of light, and you're building it using some length of the arms. Those are the characteristics of your interferometer, and they're all in this piece in parentheses. Then that property of your interferometer, L over lambda, is multiplied by this ratio of two speeds squared. One of them is the speed that you move through the ether, and one of them is the speed that light travels in the ether. So it's a comparison of two speeds, comparison of the square of two speeds. Look, speed in the denominator, the speed of light is enormous, 3 times 10 to the 8 meters per second. We're going to square it up to make it an even more enormous number. In the numerator, it's the speed that you can move your interferometer around. That's going to be way smaller. It's going to be way, way smaller. And so you're comparing, unfortunately here, to detect the ether, you're comparing a really relatively small number, the speed that you're moving the interferometer with a very, very, very large number, the square of the speed of light. And so the challenge here is that you've got to look for a small fringe shift because it's determined by this comparison of two speeds. But look, in principle here we have an experiment to detect the ether. If I move the interferometer, the light interferometer, and I see a fringe shift, then I can infer that I'm moving through the ether, I'm detecting the ether, and I could even figure out my speed that I move through the ether, my velocity through the ether. So this was the idea. Well, we want to move the interferometer as fast as possible through the ether, so we need a spaceship to move the interferometer through the ether. And Michelson realized he had a spaceship. Even though it was more than 100 years ago, he had a spaceship. He was actually living on it. It's the Earth. The Earth is a spaceship. The Earth is a spaceship that's going around the sun, and it's also rotating on its own axis. So the Earth is changing its speed through the ether on a daily and on a yearly basis. So in this picture, here is the sun. In this picture, here is the Earth and the Earth's orbit. So the Earth is orbiting the sun. We're seeing that circular motion. And the Earth is also rotating like a top. It rotates like a top once every day. It orbits the sun once every year. Both of those rotations, so this is like, why did I put this here? There's two reasons I put this picture here. You may have been on this ride. I have been on this ride. And for me, it was an awful experience. For everybody else, it seemed perfectly fine. But anyway, on this ride, these teacups rotate, and so that's like the Earth rotating like a top, and they also go in circular paths. So that's what the Earth is really doing. It's this superposition of different rotations, rotating like a top and circling around the sun. It's just that the accelerations for the Earth, we don't notice that. It's not like the teacup ride, because the accelerations are actually much smaller, but the velocities are much larger for the Earth orbiting and rotating. Okay, so there's two motions going on here, the Earth's rotation and the Earth's orbit. If there's an ether out there, so if there's a medium out there which supports light rays, which allows light rays to travel, or any electromagnetic waves to travel, then as the Earth orbits the sun, it will be traveling through that ether. And as the Earth rotates, it'll be rotating through that ether. So here I've imagined kind of the atmosphere, like I might imagine the atmosphere and the kind of the wind of the atmosphere as I move the sound interferometer through the Earth, through the atmosphere. Here I'm imagining the ether, these arrows here, And as the Earth rotates and as the Earth orbits, it's going to be moving through that ether. And sometimes it will be heading, in the direction of the ether wind, and sometimes it will be heading into the ether wind. So this is like the lifeguard swimming downstream over here on the left-hand side. This would be like the lifeguard swimming into the upstream on the right-hand side here. And so what Michelson realized was he had a spaceship. It is the Earth. It changes its speed through the ether all the time because of both its rotation and its yearly orbit, its circular motion. What are the speeds here? There's speeds that, you can't put the interferometer on a truck and drive it up and down the freeway to get high speeds. But with day and night, you can change the speed through the ether by, plus or minus between day and night, 460 meters per second. So that's a big change in speed. We are rotating fast. Between spring and fall, when we're going with the ether wind and against the ether wind, we can change it by almost 30,000 meters per second. So we can get big changes between day and night. We can get really big changes in the speed between the fall and the spring, for example, or the winter and the summer. And so the idea is to now you've got to watch the fringe pattern, and you've got to watch the fringe pattern over the cycle of a day. And if we're rotating through the ether, we'll see the pattern just sort of gently change. And we've got to, if we want really high speeds, we've got to watch the fringe pattern over a year. And over that period of the year, as we go into the ether wind and go with the ether wind, we're going to see the fringe pattern change. So this is the basic idea of the experiment. Let's see, in this example here, let's see how sensitive we are to a change in the velocity of light. So if we are on the Earth and we're kind of traveling into the ether wind, we're going to see a higher speed. If we're traveling away from with the ether wind, we're going to see a lower speed, just like traveling towards the speaker or away from the speaker. The speeds here that the interferometer is moving at is this 30 kilometers per second into the ether or away from the ether. Let's see what fringe pattern, what change in a fringe pattern that will create. See if we can calculate that. Okay. So what I'm going to use for this example is a couple of speeds. I need to use the speed that we travel on the Earth into the ether wind and away from the ether wind. So that's going to be this is 29.8 kilometers per second. So that's one speed I'm going to use in calculating the fringe shift from this motion. The other speed I've got to use, of course, is the speed of light. That's 3 times 10 to the 8 meters per second, or it's 3 times 10 to the 5 kilometers per second. So I just work in kilometers a second for this example. So there's 2 speeds I need. Then I need the information about the interferometer. We said that the interferometer is characterized by 2 things. One is the distance that the light travels from the splitter to the mirrors and back. So the distance to the mirrors is 2.4 meters, we're told. And then the other one is what is the wavelength of the light you're using, and that's 600 nanometers. So that's sort of reddish, orangey red light. And we're going to plug all of those numbers into our equation that will tell us how much the fringes will shift. It was this equation here, 2 times L over lambda, the parameters of the interferometer, times the ratio of the squares of the speed that you move with, the interferometer with, and the speed of light. It's this comparison of these two speeds. Okay, so I'm going to plug all these numbers in. I won't write them all out. But, you know, we've got the L, 2.4 meters. We've got the lambda, 600 nanometers. Obviously, I've got to plug them in the same units. So I could convert the L into nanometers or convert the wavelength into meters. I've got to then multiply that by the ratio of the squares of the speeds. I've got them both in kilometers per second right now. So I could just plug those numbers in. If I plug all those numbers in, let's imagine I did that. And then we come back like 10 minutes later. If you do it, 0.08 fringes. 0.08 fringes. So it's not even one fringe. When we talked about measuring the example measuring the wavelength of light, we had 3,400 fringes. When we talked about measuring the length of an amoeba, we had 310 fringes. So we had lots of fringe changes. The problem we're dealing with here is this comparison of the speed of our motion through the ether with the speed of light in the ether. The speed of light in the ether is so enormously large, and even using the Earth as a spaceship, our speed of motion through the ether is so much smaller. So we've got a comparison of a relatively small speed with a relatively large speed. That's what made this number small. But still Michelson realized that he could see a fringe change of 0.08 fringes. You know, that's almost a tenth of a fringe change. You can see that. If the fringe pattern moved by that, you could see that. And so, you know, he spent the year or the years to reproduce it, looking for, over that period of year, we're changing our motion by plus or minus 30 kilometers a second through the ether. He's looking for a little fringe change. I mean, I presume he's not looking constantly, but every day he goes in the lab, checks the fringe pattern. Nothing whatsoever changes. Nothing whatsoever changed. And because nothing whatsoever changed, it was, in that sense, a failed experiment. In another sense, it was the end of the idea of ether. What Michelson had discovered was that there's something very different about light compared to our everyday notions of sound. So for sound, the speed of sound is what we would call a relative quantity. The speed of sound depends on what you measure to be the speed of sound, depends on your motion through the air, which is what sustains the sound waves. The speed of light, what Michelson discovered, is not a relative quantity, it's an absolute quantity. The speed of light is always the same depending on your motion on spaceship Earth. And so the speed of light is very different. It's a huge problem to kind of understand that from the perspective of common sense. You know, if we're all different observers, if we're all moving in different ways and we measure a sound wave, the speed of the sound wave, we'd expect it to all be different because we're all observing the sound wave from our different motion. But somehow, if we're all moving around in different ways and we observe a light ray, we all measure its speed to be exactly the same. That doesn't seem logical. What we'll discover next week is that to reconcile that, the thing is we've been kind of taking space and time for granted. we do that in our everyday lives all the time, right? Space and time are important, but we don't really think about them very much.